Hello friends, IBM is here with the last episode of learning of electric fields, solved past papers. And I think we should wind up this today so that we now look forward to magnetic fields. So let's exactly begin from where we stopped last time, and I think we stopped on a certain page that I don't recall. Yes, we stopped on page 143. We had attempted this question here, and therefore we need to start from the next equation. We had attempted that one. So let us start from the next equation without wasting time. An insulated metal sphere of radius r is situated in a vacuum. The charge q on the sphere may be considered to be a point charge at the center of the sphere. State a formula in terms of r and q for the potential V on the surface of the sphere. So we want a formula in terms of r, q, and V. So we know that actually potential is given by q divided by 4 pi epsilon naught r. The mistake we normally make here is writing V as being equal to K Q over R. This is correct, but many times you'll have to define K again. So why not write the expression directly the way it appears or the way you know it in full like that? Remember, epsilon naught is permittivity of free space. Permittivity of free space. Part 2, define capacitance and hence show that the capacitance C over the sphere is given by that expression. By definition, we know that capacitance is equal to charge over potential or potential difference. And remember, potential on the sphere has been given above there, so we substitute. Therefore, this is going to be charge divided by potential, which potential is also charge, over 4 pi epsilon naught times r. Of course, you just get the reciprocal, q cancels out, and when q cancels out, then you just get this as 4 pi epsilon naught times r as the capacitance. An isolated metal sphere has that radius. Use the expression to calculate the capacitance in picofarads. So we just substitute. Capacitance will therefore be 4 pi times epsilon naught is given as 8.85 times 10 power negative 12 in the list of constants. Then times the radius, which is 45 times 10 power negative 2 to change it to meters. When I press my calculator, so pressing my calculator is giving me 5.0 times 10 power negative 11 farads. But we want the answer in picofarads. And I mentioned earlier on that when you want to bring a prefix, you divide by its value. To remove a prefix, we multiply. To bring it back, we divide by the value. And we know that pico stands for 10 power negative 12. So we divide this by 10 power negative 12, and this gives us 50 picofarads. The sphere is charged to a potential of 9.0 times 10 power 5 volts. A spark occurs partially discharging the sphere so that its potential is reduced to 3.6 times 10 power 5 volts. Determine the energy of the spark. Of course, the relationship between energy and charge or capacitance, we know that energy is given by charge half Q times V. And we have already seen capacitance is Q over V. So it means Q is going to be equal to C times V. And when you combine these two expressions, you now find that energy is going to be a half times CV squared. When you substitute this into that, energy will be a half times CV squared. I'm doing this because we don't have Q, so we need to find an expression in which all terms have been given. So when we substitute, we are trying to substitute in the formula or in the expression we have arrived at. The energy is going to be equal to a half times the capacitance, which is 50 times 10 power negative 12 times, now the potential is changing from 9.50 to 3.6. It's wrong mathematics to subtract 9.0 minus 3.6 before you square, because the potential itself is squared, not the difference that is squared. So that means we need to first of all have 9.0 times 10 power 5, and this is squared, minus 3.6 times 10 power 5, this should also be squared. Then you get the difference of the squares. When I press my calculator, so my calculator gives me energy as 17 joules. Define electric potential at a point. We know that electric potential is the work done per unit, charge in moving a positive charge from infinity to a point. The work done per unit charge in moving a positive charge from infinity to the point, that is electric potential. An isolated metal sphere is positively charged. The variation of the potential V with distance x from the center of the sphere is shown here. We see as distance x increases, the potential is decreasing. But it appears as if here the gradient is so high at that point. That means the potential starts decreasing at around that point. And this is 1, 2, 3, 4, around 5. That is 1 centimeter. So the question is, use the figure to suggest why the radius of the sphere cannot be greater than 1.0 centimeters. So why the radius of the sphere cannot be greater than 1 centimeter? If it is greater than 1 centimeter, we notice that actually the potential is decreasing. It is following the inverse, the reciprocal relationship. That is, potential is inversely proportional to the distance x. So it cannot be greater than 1 centimeter. It should be less than 1 centimeter, or should be 1 centimeter and less. And this is because inside the conductor, the potential would be constant. So inside the sphere, the potential would be constant. Yet after 1 centimeter, we see the potential decreasing. So the radius cannot be cannot be greater than 1 centimeter. Then number 2, part 2, they use the figure to suggest that the charge on the sphere behaves as if it were a point charge. Let me try to reduce the thickness. So we know that potential due to a point charge is given by the charge over 4 pi epsilon naught x. So suppose I multiply both sides by x of this expression, what happens? I want to make it look a little bit more clear. So if I multiply this side by x, I will change even the column. If I multiply this side by x and this side by x, you notice that the potential Vx is going to be equal to a constant. If I multiply both sides by x, you notice that the product V times x is equal to a constant, because this one cancels with that one, and the charge over 4 pi epsilon naught is a constant. So the whole of this will be a constant. So if we have a point charge, V times x is a constant. I'm saying V times x because they have given us potential. Next time when they give us electric field strength, we shall also still see the same thing. We would still see that if E is equal to charge over 4 pi epsilon naught x squared, that is electric field strength. When I multiply both sides by x squared and this side by x squared, I would still also argue that E times x squared is equal to a constant for a point charge, because this one cancels with that, you remain with a constant. So next time when they give us a graph of electric field strength against distance, we would still say that Ex squared is a constant, and we verify that. So let us verify that V times x is a constant. Let us start with x equals to say 2 centimeters. At x equals 2 centimeters, this is the point. The potential here is at x equals to 2 centimeters, the potential here, the scale was 4, so the potential here is 88, I guess. Let's check what that is. At x equals to 2 centimeters, product V times x is going to be equal to 88 times 2, which is equal to, this is 176. That is the product. I don't mind about the units, but this will be volts centimeters. Let's check also at x equals to maybe 6 centimeters. What is V times x? At x equals 6 centimeters, so 6 is here, so it is in the center here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So then it is in the middle here. It is in the center there. Remember, each small square is 4. So 8 times, it is 8.5 times 4. That is 34. So this is going to be 34 times 6. Times 6. Is it 34? Let me check again. 1, 2, 3, 4, 5, 6. No, it is 7.5. This is 7.5. 1, 2, 3, 4, 5, 6, 7 and a half. It is 7.5. 1, 2, 3, 4, 5, 6, 7 and a half. It is in the center there. So that is 7.5 times the scale, which is 4. This is 30. And when you multiply 30 times 6, that is 180. I hope I read the first one correctly. Let me check again. At 2, or actually at 2, it is here in the center. It's around there in the center. It's not 88. So much care is supposed to be taken here. So this is 8, 84, 88 plus 2, I think that is 90. So this should be 90, not 88. So this is 90 times 2, which is 180 volts centimeters. So you notice that actually to two significant figures, V times X is the same. So we can say that since V times X is a constant, since V times X is equal to a constant, then they are point charges. Then it's a point charge. The conclusion is the most important thing here. The conclusion is the most important thing here. So the conclusion will now, if you calculate maybe and you notice that to many significant figures the values are different, you can still suggest otherwise. You can still say not what? Not a point charge. So that one is not a big challenge. If you see that it is different, to many significant figures the values could be different. So you can still say no, it's not a point charge. Assume that the charge on the sphere does behave as a point charge anyway. Use data from the figure to determine the charge on the sphere. So we know that potential is equal to Q over 4 pi epsilon naught x for a point charge. Therefore, Q is going to be equal to 4 pi epsilon naught 4 pi epsilon naught times V times x. So we have already seen at least V times x is approximately 180, so I will just substitute. Q will be equal to 4 pi times 8.85 times 10 power negative 12, then times 180, because we have seen the product is 180, then times because the other one was in centimeters, this is in centimeters, I'm just trying to change it from centimeters to meters, so it will be times 1.0 times 10 power negative 2. Or alternatively, you can replace this you can replace value of potential with the value of x after converting it from centimeters to meters. This part here is as a result of converting from volt centimeters to voltmeters. And when I press my calculator, so from my calculator, I get 2.0 times 10 power negative 10 coulombs. An isolated metal sphere is charged to a potential V. The charge on the sphere is Q. The charge on the sphere may be considered to act as a point charge at the center of the sphere. The variation with the potential V of the charge on the sphere is shown here. You shall see many of these under capacitors. Use the figure to determine the radius of the sphere. So if we know that potential on a point charge, potential due to a point charge is Q over 4 pi epsilon naught times x, then we can try to just look for, we can just find the potential at any one point. Let's say, let me look for an easy point to deal with. Potential at 1, 2, 3. The scale here is 0.5. So I can see 16 here, 16 kilovolts, and I'm seeing Q is 3.0 times 10 power negative 8. So I'm seeing that at 16 kilovolts, the charge is 3.0 times 10 power negative 8 coulombs. So it means if I make the radius x the subject, so x or the radius is going to be, let me use r for the radius since we are used to r. So the radius r is going to be equal to, I'm making q r the subject, so it will be the charge 3.0 times 10 power negative 8 divided by, this will be 4 pi times epsilon, which is 8.85 times 10 power negative 12, then times the potential, which is 16 times 10 power 3 to change it to volts. When I press my calculator, so from my calculator, I come up with a value which is 1.69 times 10 power negative 2 in meters. Again, use the figure to determine the energy required to increase the potential of the sphere from 0 to 24 kilovolts. Let's look for 24. Remember the scale here is 0.5. So this is 21, 22, 23, 24. So this is 24. So how about if I find the area under this graph? Remember capacitance, the energy is equal to a half QV. So you can find the area under that graph. So the energy is going to be the area. Energy can be looked at as the area under the graph or the area below the line. And this is actually the same as a half Q times V, which is going to be a half. Q is 24 times 10 power 3 to change it to volts. Then, no, that is V. Then Q, corresponding value of Q is at 24. It is in the center here. It is in the center there. Remember here the scale, each small box is 0.2. So in the center is 0.1. So 4.2, 4.4, 4.5. That is 4.5. So this is times 4.5 times 10 power negative 8. So the energy here, when I press the calculator, so here I'm getting 5.4 times 10 power negative 4 joules. But see the sphere in B discharges by causing sparks. When the electric field strength at the surface of the sphere is greater than that, use your answer in B, Roman 1, to calculate the maximum potential to which the sphere can be charged. So we know that potential is equal to charge over 4 pi epsilon naught times R or times X. And we also know that electric field strength is equal to charge over 4 pi epsilon naught times R squared or times X squared. When we combine those two expressions, we notice that E is going to be, or E times R is equal to the potential. When I multiply E times R, I get the potential, so E times R is equal to the potential. Therefore, we shall say that the maximum potential V should be equal to E times R. Do not be tempted to just quote this expression. You must show that it came from those two. So the potential V is going to be equal to E, which is 2.0 times 10 power 6, then times R, and we got R as 1.69 times 10 power negative 2 from above. Then I press my calculator. So this is giving me my calculator is giving me 3.4 times 10 power 4 volts. An isolated metal sphere of radius r is given a positive charge. The distance from the center of the sphere is x. The electric potential at the surface of the sphere is V naught. On the axis, so on the surface, electric potential is V naught. Remember, on the surface, if the radius is r, that means potential at r is V naught. And remember, it is the same as that inside. So on the axis of the figure, sketch a graph to show the variation with the distance x of the electric potential due to the charged sphere for values of x from x equals to 0 to x equals to 4r. So they have told us that the potential at the surface, where at the surface the radius is r, the potential is V naught. But remember, potential is kq. I will just use k for this case, over x. So when x is equal to r, potential is v naught. Then we can, so that means, remember, potential inside is the same as that on the surface and is constant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we shall draw a horizontal line here inside. I didn't carry my ruler today, but I'll try. So using a ruler, I draw a very neat horizontal line here. That is inside, potential is constant. Then we can check what happens to the potential at 2r. So at 2r to be kq, where there is x, I put 2r, and you notice that this will be the same as a half of v naught. That means at 3r, it will be 1 over 3 of v naught. At 4r, potential at 4r will be the same as a quarter of v naught. The scale here is 0.25 divided by 10, which is 0.025. That's one small square. If I want to plot a half r, that one is easy. It is 0.5 v naught. So these are 10, these are 20. That is v naught. I think it is this point here. Yes, that is potential at 2r. Then at 3r is 1 over 3. I will divide the scale with the scale. So I will say 1 over 3 divided by the scale, which is 0.025. To get how many small squares do I need to plot 1 over 3? So 1 over 3 divided by 0.025. Those are around those are around 13 small squares. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1 over 3 is around here. This is just an estimate. Then a quarter, that is 0.25 I guess. So those are 10 small squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now using your free hand, you can do a smooth curve. You can now draw a smooth curve. So it's hard with the computer, but I'll also try. So that is the graph. So that will be the graph. Of course, it comes up to here. It is hard just to draw it. So for yours must be extremely neat. Yours must be extremely neat. And it should not go beyond the plotted, the required points. Okay. It is a smooth curve, not a straight line. So you should be very careful with that. Part B. The electric field strength at the surface is E naught. Note that electric field strength is given by kq over x squared. Remember, here I don't need the k for now, so it's just a relating. So if I have on the surface E is at the r, so this will be kq over r squared, which is given as E naught. So sketch a graph to show the variation with distance x of the electric field strength due to the charged sphere for values from the center up to 4r. So at a distance of 2r, we shall have where there is x squared, we shall put 2r, that will be kq over 2r, and it is squared, and that becomes 4r squared. So this becomes 1 over 4 of E naught. Then we can even check at 3r. That will be kq over 3r squared, which becomes 1 over 9 of E naught. We can check E at 4r, which will be kq divided by 4r. This is squared, which becomes 1 over 16 of E naught. The scale has not changed, it's still the same. So the scale is 0.025. We divide this by 10 because there are 10 small squares. So we can start. Inside the conductor, remember E is 0, so we draw a horizontal line along the x-axis. Use a ruler, you draw a horizontal line along the x-axis because E is 0. Then E on the surface is Inode, so I have to look for the surface. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is the surface. So I will draw a vertical line here. To define a boundary, I'll just put here a vertical line just to make my work look neat. Okay, that is perfect. Then we shall now plot a quarter. At 2r, it is a quarter. Those are 10 small squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is a quarter. Then 1 over 9 at 3r, you divide 1 over 9 by the scale. 1 over 9 divided by the scale, divide by 0.025. So 1 over 9 divided by 0.025. Those are 4 small squares. So this is 1, 2, 3, 4, around 4.4. Then 4r is 1 over 16. 1 divided by 16. Then divide by the scale, 0.025. Those are 2.5 small squares. So this is 1, 2.5. So now we draw our graph passing through all these points, a smooth curve. It should not be a straight line. So maybe I can start from this side. It's not easy on a computer, but you can draw better than mine. No problem. It is a smooth curve which goes through those important points that we have plotted. So I expect that you should draw a better curve than mine. Smooth curve. It should be smooth. So that will be the graph. It should be smooth, a smooth curve. Me, I can't draw it smooth when I'm on a computer, but at least the shape is the same. Next, a helium nucleus contains 2 protons. In a model of the helium nucleus, each proton is considered to be a charged point mass. The separation of these point masses is assumed to be that one. For the 2 protons in this model, calculate the electrostatic force, that is the force due to the charges. So the force due to the electric charges is going to be the product of the charges divided by 4 pi epsilon naught times x squared. That is according to Coulomb's law. So we are now substituting. I will just use 1 over 4 pi epsilon naught, which is k, which is 8.99 times 10 power 9. That is 1 over 4 pi epsilon naught. If you want, you can substitute epsilon naught, no problem. Then times the product of the charges, that is 1.6 times 10 power negative 19, and this should be squared, divide by the square of the separation, which is going to be 2.0 times 10 power negative 15 squared. Do not be lazy not to think that to begin wondering where 8.99 times 10 power 9 came from. I have said 1 over 4 pi epsilon naught is the same as 8.99 times 10 power 9. And we saw this when we were dealing with the lessons, so you must be familiar with it. When I press my calculator, so pressing the calculator gives me 4.7, no, not 4.7, Pressing my calculator is giving me 58. You should also be pressing the calculators before you wait for mine. 58 newtons. Then the gravitational force. So the gravitational force due to gravity, is G, product of the masses m1, m2 over x squared. So G is the gravitational constant, which we already know as 6.67 times 10 power negative 11 from gravitation, times 1.67 times 10 power negative 27. This is square, that is the mass of the proton, divide by the square of the separation, which is 2.0 times 10 power negative 15, and that is squared. So I press my calculator. You can also press yours if you are following carefully. So from my calculator, I get 4.7 times 10 power negative 35. You see how small Fg is compared to electrostatic force, the force due to the charges. Use your answer in A. Using your answer in A suggests why there must be some other force between the protons in the nucleus. In fact, you realize that actually the electrostatic force is far, far bigger than the gravitational force. The electrostatic force is far, far greater than the gravitational force, yet the gravitational force is attractive. That one we know from gravitation. The electrostatic force is repulsive, yet the electrostatic force is much greater than the gravitational force. So the repulsive force is much greater than the attractive force. Yet we know that the protons inside the nucleus still exist together. So there must be another force holding them together. There must be another attractive force holding the protons inside the nucleus together. So we are saying force of repulsion, which is the electrostatic. The force of repulsion is much greater. Is much greater than the force of attraction. The force of repulsion is much greater than the force of attraction. The force of repulsion is this one here. Yes, the force of attraction is this one here. If the force of repulsion is much greater than the force of attraction, yet the protons exist inside the nucleus, there must be another force. So we are saying there must be some other force which is attractive. There must be some other force of attraction. There must be some other force of attraction. There must be some other force of attraction responsible for holding the nucleus together. Responsible or to hold the nucleus or the protons together inside the nucleus. Some other force of attraction to hold the nucleus together. Perhaps this is the strong nuclear force. That could be the strong nuclear force. That could be the strong nuclear force. Okay. Then using your answer in A again suggests why the additional force must have a short range. Of course, that is obvious. If it was a longer range, then it would mean because outside the nucleus there is a repulsion between protons. Therefore, if it wasn't short range, then it would mean that maybe protons would just stick together, and therefore it should be short range so that all nuclei do not stick together. So I am saying outside the nucleus, there is a repulsion between protons. Outside the nucleus. Outside the nucleus, there is repulsion. There is a repulsion between protons. So the attractive force must act only in the nucleus. So attractive force must act only in the nucleus. Alternatively, we would think about this as if it wasn't short range, if not short range, if it wasn't short range, all nuclei would then stick together. All nuclei, I want to write nuclei for plural of nucleus. If it wasn't short range, all nuclei would stick together. Therefore, this force should be short range. State the relationship, the relation between electric field strength and potential V. Now we are familiar with this, and we know that field strength is equal to the negative potential gradient. Field strength equals to the negative potential gradient. Field strength equals to the negative potential gradient. Two positively charged metal spheres A and B of diameters 18 and 12 respectively are isolated in space, as shown here. So we have sphere A, we have sphere B, the diameters have been given, so you can think about the radius as this being 9 centimeters, and the radius of this as being 6 centimeters. The centers of the spheres are separated by a distance of 50 centimeters. Point P is at a distance x. You can think of the distances between the centers. If that is 9, the other one is, okay, it is 50. Point P is at a distance x from the center of sphere A, as we can see here, along the line joining the centers of the two spheres. The variation with x of the electric potential V at P is shown here. So this is the variation. I can try to reduce this so that the graph is on the page. State qualitatively and explain the variation with distance of the force on a proton placed at point P, where x varies from 10 centimeters to 41. So I think 41 here on the bottom, the scale is 1 centimeter. I think 41 is around here. And we notice that the minimum point here is 30. Actually, this is 35, I think. Then 10 centimeters is just around here, where we see that the gradient is almost steepest. So this is where we have 10 centimeters. So we want the variation of the distance of the force. Recall that electric field strength is the negative potential gradient, negative dV by dr. And recall that electric field strength is the force acting on a unit charge. So it means E is directly proportional to F. E is directly proportional to F. The magnitude of E is directly proportional to F. But note that between 10 centimeters and 35, the gradient is decreasing, but it is positive anyway. Repulsive forces are positive. If the gradient is decreasing and it is negative, it means E is positive. Between 10 centimeters to 35, gradient is negative. The gradient is negative, which means E is positive because E is the negative gradient. So E is positive. That's number one. That means the force is positive, and positive forces are repulsive by convention. So this force is repulsive. I repeat this, between 10 centimeters and 35, the gradient is negative. The gradient of potential with distance is negative, but E is the negative gradient. So if the gradient itself is negative, E becomes positive, which means force is positive. By convention, positive forces are repulsive forces. By convention, it is repulsive forces that are assigned positive. Then at 35, the gradient is 0. At 35, the gradient is 0, meaning E is 0, the force is 0. So at that point, because here the gradient was decreasing, the force was decreasing, and at 35, the force is 0 because the gradient is 0 since E is 0. Then between 35 to 41, the gradient is increasing. So 35 to 41, the gradient is positive and is increasing. So it means E is now going to be negative, which means F is actually negative. So that means the force is attractive. The force is attractive, or the force is increasing in the opposite direction. That's what we can say. So let us put this in the explanation. And by the way, the force is maximum at 10 centimeters because the gradient is maximum there. It goes on decreasing. It's almost a straight line around 10 or close to 10 centimeters from the surface. So we shall simply say that at x equals to 10 centimeters, the force is maximum because the gradient is largest. The force is maximum and the gradient is largest, but the force is also repulsive, or it is actually to the right, because the sphere and the proton have the I think they have like charges. The sphere, and because from the potential you see that the potential is always positive, so it means the sphere and the proton are both positive. So that is also even enough to tell us the force is repulsive. It is actually repulsive to the right, because if a proton is brought here, then the force is going to be repulsive to the right. It is repelled to the right. The force is repulsive to the right because the sphere and the proton have like charges. Okay, those are almost, I think those would be almost 3 marks. Saying that the force is maximum at 10, it is repulsive. And why it is maximum is because the gradient is largest. Those are almost 3 marks. Okay, then let's continue. But as x increases, the force decreases. So as x increases from 10 to 35, as x increases, the force decreases. As x increases, we are seeing that the force decreases, and the force becomes 0, and becomes 0 at x equals to 35 centimeters. Note that at 35, the gradient is 0. At 35, the gradient is 0. Then what happens after 35? So as x increases from 35 centimeters to 41 centimeters, the force increases in the opposite direction because the gradient is increasing, so the force is increasing. So the force increases in the opposite direction. So that would give you this full 6 marks. That would give you the full 6 marks. If I want to show, if you want to be showed how, saying that x increases as the force decreases, that is a very important mark. And saying that it becomes 0 at x equals 35, that is very important. And as x increases from 35 centimeters to 41, the force now increases in the opposite direction. That is very important. Okay, so those will be the 6 marks. State a similarity between the gravitational field lines around a point mass and the electric field lines around a point charge. They have not specified the polarity of the charge, so we can simply say both field lines are radial. Both have radial field lines. Both have radial field lines. Okay, the variation with the radius r of the electric field strength E due to an isolated charged sphere is in a vacuum is shown here. So they have given us E with distance in a vacuum, and that is how it varies. We are used to such graphs. Use the figure to state the radius of the sphere. You just come here. Inside the sphere, E is 0. So where does E stops being 0? So the scale here is 0.1. So this is 2.1. So the answer here is going to be 2.1 centimeters. The reason E is equal to 0 inside the sphere. So the radius is 2.1. Then use data from the figure to calculate the charge on the sphere. Charge on the sphere. So we can use straight away we can use E is equal to charge over 4 pi epsilon naught x squared. I want the charge on the sphere. So you will notice that when the radius at the surface, that is for r of the radius equals 2.1 centimeters, the electric field strength on the surface equals to, let's find E on the surface, it is 1.3 times 10 power 5 from the graph. It is 1.3 times 10 power 5 on the surface, times 10 power 5. So on the surface, for radius equals 2.1, E is 1.3 times 10 power 5 times 10 power 5 volts per centimeter, volts per meter. So we can now substitute or make Q the subject. So charge is going to be equal to 4 pi times epsilon naught, which is 8.85 times 10 power negative 12. Then times x, which is 2.1 times 10 power negative 2, and this is squared, that's the radius, times electric field strength, which is 1.3 times 10 power 5. I now press my calculator. So from my calculator, I'm getting Q as 6.4 times 10 power negative 9 coulombs. Use the formula for the electric potential due to an isolated point charge, or using the formula for the electric potential due to an isolated point charge, determine the capacitance of the sphere. By definition, we know that capacitance is charge over potential difference, and we now know that potential is actually Q divided by 4 pi epsilon naught x. When you combine the two expressions, you notice that capacitance will now become 4 pi epsilon naught times x. And when we substitute, we have 4 pi times epsilon naught is 8.85 times 10 power negative 12 times the radius, which is 2.1 times 10 power negative 2. We now press the calculator. So from my calculator, I get capacitance as 2.3 times 10 power negative 12. You can also check. An isolated metal sphere of radius r is charged so that the electric field strength at its surface is E naught. At the surface, E is E naught. So E at a distance r is the same as E naught, but this is the same as kq over r over x squared. Where there is x, I just put there r. That is E naught. Sketch the variation of the electric field strength E with the distance x from the center of the sphere. Your sketch should extend from x equals 0 to x equals 3. Remember, inside the conductor E is 0, so we draw a horizontal line along the x-axis. Use your ruler. Draw a beautiful horizontal line along the x-axis. And on the surface E is E naught, so I'll draw a vertical line here, as always. To make this look very beautiful, I'll draw a vertical line on the surface. Okay, that is just along the surface, and E is at the surface is that. Then E at a distance of 2r. We can check E at a distance of 2r is going to be kq over 2r, but this is squared, which becomes a quarter of E at the surface. And E at a distance of 3r is going to be kq over 3r, and this is squared, which becomes 1 over 9 of E at the surface. So we can use the scale. I think this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So those are 30. The scale will be 1 over 30. I'm trying to find the value of one small square. That is 1 over 30. Now if I want to plot a quarter, I'll just say a quarter divided by the scale, which is 1 over 30. So a quarter, that is 1 over 4, divided by the scale, which is 1 over 30. So this gives me 7.5 small squares from the base. So that is 1, 2, 3, 4, 5, 6, 7. 7.5, that's where our graph will pass. Then 3r is 1 over 9, so I will say 1 over 9 divided by my scale, which is 1 over 30. So 1 over 9 divided by the scale, which is 1 over 30. And this is around 3.3, that is around 3.3 small squares around there. So we now draw our graph going through those points. It is a smooth curve. So a smooth curve is easier to draw when you start from the bottom and your free hand moves downwards. Your free hand moves downwards, something like that. So for yours, you should be, maybe I can redraw a better one, better than this one. Let me increase the thickness. Okay, so something like that. Something like that would be good. So yours should be a very smooth curve. Then next, the de Broglie wavelength. The de Broglie wavelength of a particle is lambda naught. The de Broglie wavelength of a particle is lambda naught. This is in quantum physics, I guess. Although just for completeness, we can answer it here, but I know we answered it in quantum physics, or we shall answer it in quantum physics. The de Broglie wavelength of a particle is lambda naught when its momentum is p naught. If you recall the formula, de Broglie wavelength, lambda is equal to h over momentum. So they are saying when p is equal to p naught, lambda is equal to lambda naught. When p is p naught, lambda is equal to lambda naught. That means lambda naught is equal to h over p naught. Then on the graph, sketch the variation with momentum p of the de Broglie wavelength of the particles for values of momentum from p naught over 2 over p naught. So when p is p naught, lambda is lambda naught, so we plot this point. I think that is the point. When p is p naught, lambda is lambda naught. That is the point. So we have plotted p naught against lambda naught. Then we need to find what lambda is when p is p naught. So for p equals to p naught over 2, lambda is going to be equal to h divided by p naught over 2. The 2 goes up, so lambda becomes twice h over p naught, which is the same as twice lambda naught. So at p naught, I look for twice lambda naught. At p naught, you look for twice lambda naught, which is, I think, that point there. You can put a ruler and be very sure, but I think it's that point. I can also check at the center of these two. At the center of these two, which will be 3, I want to check p equals to 3 over 4 of p naught, because this was a half. Then how about if it is 3/4? That is in the center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is in the center there. So in this case, lambda is going to be equal to h divided by 3 over 4 p naught, which becomes 4 over 3h over p naught, which is 4 over 3 lambda naught. And 4 over 3 is around 1.33 lambda naught. So I'm now going to plot a point where this is 3 over 4 p naught, and it is 1.33. So the scale here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think those are 20 small boxes, so the scale is 1 over 20. So I'll say 1.33 divided by 1 over 20 to get the number of small boxes. When I press my calculator, and these are almost 27 small squares from the base. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, around 27. So this will be the point, somewhere there, around 27. So this will not be a straight line, of course. It will be a smooth curve through those points. So I will draw a smooth curve. I will draw a smooth curve through those points. It can't be a straight line. Okay, using a pencil, you should be able to draw a better curve than mine. You should be able to draw a better curve than mine. It is not a straight line. I repeat that. It is not a straight line. It is not a straight line. It is not a straight line. From what I've seen, it is not a straight line. It is a curve. So you must draw a very neat curve, extremely neat. And it's better when you plot the points. It's better you plot the points. Okay, next, a radioisotope decays with a half-life of 15 seconds. Radioisotope decays with a half-life of 15 seconds to form a stable product. A fresh sample of the radioactive isotope at T equals 0 contains N0 nuclei and no nuclei of the product, of the stable product. Sketch the variation with time t of the number n of nuclei in the stable product for time t equals to 0 to time t equals 45. So the half-life is 15. So let's find, I'm going to simplify, use a simple, this is going to be the parent. Let's say this is the parent. That is the parent. Let this one be the product. After time, I would have started with time. Let me put time at the end. So at time t equals to 0, the parent is n naught, the product is 0. That is at t equals to 0. Then at time t equals to half-life, that is after 15, the parent is n naught over 2, it has reduced to half. Of course, the product will also be simply n naught over 2. Then at t equals to the second half-life, that is after 30, the parent reduces again by another half, it becomes n naught over 4. Then the product, when the parent reduces by n naught over 4, the product must be increasing. So the product becomes now 3 over 4 of n naught. Then at time t equals 45, when the parent reduces to 1 over 8 of n naught, you go on dividing by 2. Then the product must therefore be 7 over 8 of n naught. So we just plot these points. So the graphs are meeting at t equals to 0. I mean t equals to first half-life. So you look for first half-life, that is at 15, and I think this is the point. Sorry, it is at slightly below. Fifteen is here. 15 is there. Of course, when t is equal to 0, everything is 0. I mean, when t is equal to 0, the product is 0. Then when t is 15, the product is a half. When t is 30, the product is 3 quarters. 3 quarters, that is 7. 3 quarters, 3 divided by 4, that is 0.75. And 0.5, remember here the scale, these are 20. The scale is 0.5 divided by 20. I'm finding the scale. 0.5 divided by 20. The scale is 0.025 for each small square. Now I want to plot 0.75. That is 3 over 4. So I say 0.75 divided by the scale. So divide by 0.75 divided by 0.025. Those are 30 small squares. So since these are 40 squares, I leave 10 from the top. To simplify life, I'll leave 10 from the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 3 over 4 n naught. Then 7, I have 7 over 8. I divide this again by the scale, 0.025. So 7 over 8 divided by 0.025. That is 35. So I leave 5 from the top. 1, 2, 3, 4, 5. That is the point. So we have 1, 2, 3, 4 points. So I will draw a smooth curve of that nature going through all those points. So draw a smooth curve which goes through all those points. Very smooth, as I have tried to draw it. So that is the graph. An isolated metal sphere of radius r is charged so that the electric potential at its surface is V naught. So potential at the surface is V naught. And without wasting time, potential at the surface is V naught, which is given as kq over x. And here x is just r. And the potential at the surface is the same as potential inside. So we look for r and we draw a horizontal line along V naught. Potential is constant inside and is the same as the surface. Then at 2r, potential at 2r is simply equal to kq over 2r, which is a half of V naught. Potential at 3r is simply kq over 3r, which is a third of V naught. So at 2r, it is just a half, which is easy to plot. I think this is the point. A half is the point here. Then 3r, here I will use the scale for 3r. 3r, the scale here is 0.5 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are 15. So it's 0.5 divided by 15. That is the scale. So 0.5 divided by 15. That is the scale. Then I have 1 over 3. 1 over 3 divided by my scale. Those are 10 small squares. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got 1 over 3. I divided by the scale, and it is 10 small squares. So we have 3 points to join. So I will join this point, that point, to that point, so that I have a smooth curve. I will redraw this to make it better, maybe. Okay, so that is the beautiful curve. Photons having wavelength lambda are incident on a metal surface. The maximum wavelength for which there is emission of electrons is lambda naught. For photons of wavelength lambda naught, the maximum kinetic energy is Emax. Now this is quantum physics, but just for completeness, because the graphs were together, we shall not separate them. Sketch the variation with wavelength of the maximum kinetic energy for values of wavelength between lambda equals to that and lambda equals to lambda naught. So let's have the theory at the back of our minds so that we can draw correct values. We know that the energy of the photon, which is HF, is given by HF naught plus the maximum kinetic energy, which I'll call E. And this means Hc over lambda, because they have given us in terms of wavelength, is equal to Hc over lambda naught plus E. So we can check. When lambda equals to lambda naught, of course, this will be 0. For lambda equals to lambda naught, E is going to be 0. So at lambda naught, the graph will be at the x-axis. So the first point we are going to plot is lambda naught against 0. We can now check at lambda naught over 2. If lambda is equal to lambda naught over 2, what is E? We are substituting. What is E? We substitute in this equation here. So we shall say Hc, the 2 goes up, it becomes twice Hc over lambda naught minus Hc over lambda naught is equal to E. This gives us Hc over lambda naught to be equal to E. And they said lambda naught for wavelength equals to lambda naught over 2, the maximum kinetic energy is Emax. So E here is Emax. So at lambda equals lambda naught over 2, we have Emax. So this is the point here. I think it is this point here. You put a ruler to be very accurate. So that is the point. Then we can still check for lambda naught over 3. If wavelength is lambda naught over 3, what is E? So we know that the 3, when we substitute, the 3 will go up. So it becomes 3hc over lambda naught minus hc over lambda naught being equal to E, which gives us twice hc over lambda naught. And note that hc over lambda naught is actually Emax. So this is going to be twice Emax. So this will be twice Emax. So this is in the center. So this is in this point here. So we have those 3 points, and when we join them, you see that they are going to form a curve. So we shall draw a smooth curve. Yes, we shall draw a smooth curve like that. Okay, so as simple as here, you don't guess, of course. Here you don't guess. You must just come up with the real points, because that's why I've been doing all this theory. Just substituting this equation here, trying to subtract so that I check and compare with the quantities that have been given. So that is the curve you would come up with. Okay. A pure sample of a radioactive isotope contains N naught nuclei. The half-life of the isotope is T1/2. The product of the radioactive decay is stable. The variation T with time T of the number of nuclei of the radioactive isotope is shown here. So this is the parent. On the time axis, the time T on the figure label on the time axis, the time T equals to 1.0 half-life, and the time T equals 2.0 half-life. We can even label even 3. So we've put here a ruler along the half of the parent nucleus, and this will give us the half-life. So this will be 1.0 T1/2. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Since half-life is constant, so we shall count another 20 for the second half-life. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That is the second half-life. So I'll call this one T.0, T1/2. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This will be 3.0 T1/2. That is the third half-life. We can stop there. So this is the third half-life, second, first. Now sketch the variation with the time T of the number of nuclei of the decay product from T equals to 0 up to T. So we can now check. Of course, we know from one of the graphs, I'll call this one parent, I'll call this one product, and I'll call this one time T. Initially, when the parent is N naught, the product is 0, the time is 0. Our graph starts from here. That one we have seen. Then, when time is half-life, first half-life, that is just T1/2, the parent reduces by 2, that is N naught over 2. Of course, the product will also be a half of the parent. So that means our graph will meet this point here at T equals to 1/2. For the second half-life, T is 2/2, the parent reduces to 1/4, N naught over 2, the product goes to 3 over 2 of N naught. The other one decreases, so this is 3 over 4, not 3 over 2. 3/4, that is 0.75. And here, when I check the scale, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are 20. So they are 40. And I want 3/4 of 40. I think that is 30. I leave 10 on the top. Along with 2.0, I'll leave 10 on the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 7 over that is 3/4, I think. Yes. So this is the point, 3/4. Then when the parent reaches, this was n naught over 4. When the parent now is n naught over 8, the product is 7/8 n naught. And 7/8 n naught, when I divide by the scale, 7/8. Divide by 1/20. That is 17. Now divide by 1/40. So here we leave 5. At 3 third half-life, we leave 5. 1, 2, 3, 4, 5. So we leave 5 on top. So the rest we just extend our graph. So I'll draw a smooth curve in these points. So for you, draw a very smooth continuous curve without kinks. Okay, so that is going to be the graph of the product. So when the time is 3 half-lives, that 3t1/2, not 3t/2. This reduces to a eighth, the other one increases to 7/8. Okay. Define electric potential, work done per unit charge to move a positive charge from infinity to the point. Work done per unit charge to move a positive charge. To move a positive charge from infinity to the point. Two-point charges A and B are separated by a distance of 12 centimeters in a vacuum as illustrated here. The charge of A is this. A point P lies on the line joining charges A and B. Its distance from charge A is x. The variation with the distance x of the electric potential V at a point P is shown in the figure. So this is potential. You see that potential is changing signs, meaning that the charges are actually going to be unlike charges without even hesitation, because the potential changes signs. If the potential changes signs, it means because the charges have opposite signs. Because if the potentials are like the charges are like charges, the potential will always be either positive or always negative. Use the figure to determine the charge of B. Use the figure to determine the charge of B. They have told us at a point P lies on the line joining charges A and B. Its distance from the center A is x, and they have given us the variation here. So we want to find the charge of B. We want to find the charge of B, but there is a point between the charges where the potential becomes zero. There's a point between the charges where the potential becomes zero. So it means at that point, when we sum up the potentials, the total is zero, so we can find the charge. Let's use that point. So at x equals to 4 centimeters from A, the total potential is zero. So we can use that point. Remember, potential is given by charge divided by 4 pi epsilon naught x. So I'm now substituting. For A, the potential will be, the charge is 2.0 for A. just from the charge for A has been given as 2.0. So say 2.0 times 10 power negative 9 divided by 4 pi. I don't even need to simplify 4 pi. I'll just put it here, 4 pi epsilon naught times the distance is 4 centimeters. That is 4 times 10 power negative 2. That is from the center, plus I add the potential for the other charge, which is not known. So I'll say Q over, again, 4 pi epsilon naught. But the distance from 4 centimeters to the other charge is, because the separation of the charge is 12, so from 4 to the center of the other one, that is 8 centimeters. So this will be 8 times 10 power negative 12, and when you sum up the potential, you will get 0. So when I factor out here, 4 pi epsilon naught disappears when I take it the other side, and therefore I remain with I'm remaining with 2.0 times 10 power negative 9. This algebra is not part of physics, so 4 times 10 power negative 12 plus Q over 8 times 10 power negative 12 is equal to 0, because 1 over 4 pi epsilon naught is a common factor, so it has disappeared. So making Q the subject, I'm simply making Q the subject by saying Q is equal to, when I take the other on the other side, it will be negative 2.0 times 10 power negative 9 over 4 times 10 power negative 2, then times 8 times 10 power negative 2. This is not negative 12, it's negative 2. To change it from centimeters to meters. So I simply press my calculator, I see this cancels out, so the answer is negative 4.0 times 10 power negative 9. Okay, so that is the charge. That is the charge Q. Then the electric potential, use the figure to determine the change in electric potential when point P moves from the position where X is 9 centimeters to where X is 3 centimeters. 9 centimeters, I think it is in the center here. 1, 2, 3, 4, 5. 9 centimeters is here. 9 centimeters. 9 centimeters. I think that is negative 10. And to the point where X is 3 centimeters. 3 centimeters. 1, 2, 3, 4, 5. 3 centimeters here. This is 3. This was 9. So 3 centimeters is here. The potential is, each small square is 1, so the potential is 2. That is, so we have 2 minus negative 10, which is actually 12 times 10 power 2. That is the change in potential. So the potential is 2 minus negative 10 times 10 power 2, which is 1200 volts. That is the change in potential. An alpha particle moves along the line joining point charges A and B. The alpha particle moves from the position where X is that and reaches where X is that. So the change in potential is 1200. Use your answer in B Roman 2 to calculate the speed V of the alpha particle at this position. So the alpha particle is positively charged, and at this point, it is moving from negative potential to positive potential. So it is gaining kinetic potential energy as it loses kinetic energy. So we shall say loss in kinetic energy is equal to gain in potential energy. So we are simply going to say a half mv squared is equal to q times change in potential. So I'll simply substitute a half times the mass. It is an alpha particle. Remember, the mass is 4u, the charge is 2e. So it is a half times 4 times 1.66 times 10 power negative 27 to change it to kilograms, then times v squared being equal to the charge of an alpha particle, which is 2e, that is 2 times 1.6 times 10 power negative 19, then times the change in potential, which is 1200. Here we just press our calculator straight away. So remember, this is small v, which is speed. So when I divide to make v the subject, I'm getting 3.4 times 10 power 5 meters per second. State what is meant by a field of force. I think this is another time we are seeing this question. A field of force, that is a region of space. Region of space. A region of space where a particle experiences a force. Experiences a force. That is a field. Now here we cannot be very specific because we don't know whether it is an electric, magnetic, or gravitational. So it must be general, a region of space where a particle or a body experiences a force, as simple as that. State one similarity and one difference between the electric field due to a point charge and the gravitational field due to a point mass. Earlier on, we have seen that both field lines are radial, or both fields are radial. So we can say both fields are radial. Both fields are radial, or both fields decrease with distance. When we say both fields are radial, we actually mean both fields decrease in strength with the distance. In other words, both fields, or they both have an inverse square variation with distance. Or you would say both have an inverse square relation with distance. An inverse square variation with distance. All those points almost mean the same thing, so you don't need to keep repeating yourself. Then difference, we know that the gravitational field is always towards the mass. The gravitational field is always towards the mass. For the electric field, since we have both positive and negative charges, the electric field can be towards or away from the charge. Electric, I'll say, and electric field. The electric field can be towards or away from the charge. It can be towards or away from the charge. And part B, this is the last question, of course. In part B, an isolated solid metal sphere of radius 0.15 is situated in a vacuum as illustrated here. The electric field strength at the surface is 84 volts per meter. Determine the charge Q on the sphere. So we want to determine the charge Q on the sphere. So we know that electric field strength is given by the charge over 4 pi epsilon naught x squared. So I want Q. I'll make Q the subject. So Q will be equal to 4 pi times epsilon naught, which is 8.85 times 10 power negative 12, then times x, which is 0.15 but is squared, then times E, which is 84 volts per meter. So I press my calculator. So from my calculator, I am getting this as 2.1 times 10 power negative 10. So the charge is 2.1 times 10 power negative 10 coulombs. Don't always forget to write the final answer on the space provided. Then part 2, the electric field strength at point P, a distance x equals 0.4 meters, 45 meters from the center of the sphere. So if we simply say that E is equal to a constant k times q over x squared, we have seen that when E is 84, this is equal to times k times the charge, which is 2.1 times 10 power negative 10 divided by the radius, which is 0.15 squared. That is one equation. Then when the electric field strength is not known, now we'll call it E at a distance x. This will also be equal to k times the charge, which is 2.1 times 10 power negative 10 divided by the distance, which is 0.45 squared. When we divide the two equations, so we shall have Ex over 84 is equal to k cancels, 2.1 also cancels. So this will be 0.15 over squared over 0.45 squared. When you press your calculator when making Ex the subject, so pressing the calculator, this is giving me a 9.3. Alternatively, since you have the charge, you would just substitute for the charge, and then you substitute also epsilon naught. That is, you would use the formula directly as E is equal to Q over 4 pi epsilon naught x squared. You have got the charge. You have now the radius. You would find E by substitution. That would be another way of doing this. Last but not least, use the information from B to show on the axis the variation of the electric field strength E with distance x from the center of the sphere for values x equals to 0 up to 0.45. So from the center, we know the radius. The radius is 0.15. So when the radius is 0.15, then when x is 0.15, E is 0. That is inside. So that is 0.15, 1, 2, 3, 4, 5 here. We draw a horizontal line along the x-axis for 0.15. Use a ruler to draw a beautiful horizontal line along the x-axis. Then on the surface, we have seen that on the surface it was 84. So we shall plot 0.15 against 84 again. So we look for 0.15 against 84 on the surface. The scale here is 2. So 0.15, I will draw a vertical line along 0.15 for simplicity. So 0.4585, 85 is 1, 2. I think there are only two small boxes. I'll ignore this part here. It starts from here. That is 84, somewhere there. And I'll look for the other one is at 0.45. It is 9.3. So I'll look for 9.3. Remember the scale is 2 centimeters. I mean 2 volts per meter. I hope I plotted 84 correctly. Yes. Now I want to plot 9.3. So I plot 0.45 against 9.3. 0.45 is in the center. 1, 2, 3, 4, 5. 0.45 is there. 9.3, this is 2, 4, 6, 8. 9 is in the center here, so 9.3 is around there. So I know that this is a smooth curve. If you want, you can check at 2, you can check at 3, 0.3. You can check at any other point. You can check all those points, but I know those are enough points for me to draw a smooth curve. So I will draw a smooth curve, something like that. I will draw a smooth curve, something like that, through those points. If you want to check, you can check at 0.3, you can check at 0.2 so that you have a more perfect curve. Okay, thank you very much. That is the end of electric fields officially. Next, we shall be looking at magnetic fields and electromagnetic induction. Thank you. I hope you have enjoyed this, and I wish you a good day.